Good morning, good afternoon, and good evening, everyone. And today we're going to be continuing our lesson on tangent planes and line approximations. So we've done deriving a tangent plane equation based on some information we already know about partial derivatives, about equations of planes given a point on that plane. And yeah, let's go ahead and do linear approximations here. So linear approximations. What does this mean? It means approximating a line, obviously. So if we look at our previous example, um, in example one, we found an equation of the tangent plane, the graph of a function. Where's our example one? Example one, there we go. We found our equation to the tangent plane given an elliptic paraboloid and a point, a specified point. Um, what else? And we found it to be, oh, there, this thing, right? That's our tangent plane formula. And therefore, in view of visual evidences, well, from there, we can actually find a line function of two variables. Let me just do this. We can actually simplify this thing to be, so that here we want a simplification. Z equals 4x plus 2y minus 3. Let me actually check if this is correct. This is 4x minus 4, 2y minus 2. This is 4x plus 2y minus 6. I put my z to the other side. I get negative 6 plus 3. Also, yeah, that's correct. So here they want it simplified. And using this idea, so an example, well, the linear function, so here we can have a linear function of two variables. And funny enough, and we're still going to try to figure out why. It's the same as the tangent plane equation. So it's going to be L of xy of this thing, 4x plus 2y minus 3. Right? And we're saying this is a good approximation. So this is a good approximation to f of xy when that particular point xy is near 1 and 1. So what is this? The function L is called the linearization of f at 1, 1. So we're saying in high level terms, function L is linearization of our original f function at 1, 1. And the approximation is that function itself. So our function itself, that's why we're going to put this two squiggly equal signs. I forgot what you call them. And there we have it. My bad, this is minus 3. So this is the linear approximation or tangent plane approximation. So they're actually the same thing, right? So we call this the linear approximation or tangent plane approximation, right? Um, okay. Okay. I hope that makes sense. Mm, mm. Okay, I'm not gonna go through the example, but I was debating whether to go through it or not. So we call this again the linear or tangent plane approximation. That's what we call that. So in general, let me do this. We know from number two, where's our number two? Oh, the equation of the tangent plane. So we know the equation of the tangent plane to the graph of a function f of two variables, right? So we know, okay, my u looks like a, so we know tangent plane equation. And we're gonna specify it at a particular point. So of function f of two variables, and we're going to specify it at this point. A, B, and then the other one is f of A, B. So we're assuming our points are A, B. And it's the following. Our output z, which is a function of AB, plus our f sub x. So we're taking its partial derivative with respect to x. X minus a, so that x coordinate, plus f sub y of AB. This time y minus b, right? And this is just general from here, from this thing that we got. This is the general formula, right? And so the linear function whose graph is this tangent plane. So namely, so we're going to do L of x, y. And this is, well, we just copy paste what we did a while ago. F sub x at that point, my f sub y at that point, right? So that's just my, no, that is the linear function with the graph of the tangent plane, right? I hope that makes sense. So just to go back, we did talk about tangent planes. We were able to find the equation of a tangent plane given some point and their partial derivatives. And from there, once we simplify that thing, well, we can actually get the linear function. And we say that it's a good approximation to our original function of two variables. So there's well, honestly, this is just the surface, the quadratic surface. So it's a good approximation to that surface function when our xy is near some specified point. And so we say that L is the linearization of f at that point, and the approximation is just f. And so we did a general idea here where our output is z, which is equal to my function at AB. And this will give me two things to consider, or two lines, right? And there we have it. That's the formula. Okay, just closing the gap there. Okay. What else can we say? So that's called the linearization of f, and the approximation as well. Let me just continue this. There we go. That's the approximation. Right? Yeah. So this is called the linear approximation or the tangent plane approximation of f at AB. And so we have defined tangent planes for surfaces z equals fxy, where f has continuous first partial derivatives. But what if, okay, so here are the, here's the question. So we were able to define tangent planes because we have continuous partial derivatives, first partial derivatives. But what happens if our f sub x and y are not continuous? Will we still be able to define tangent planes? So what if f sub x and f sub y are not continuous? Will we still be able to define tangent planes? Will we still be able to make linear approximations or linearizations in that sense? Well, we're gonna find out. We're gonna see if we can still do it. Well, here we have a piecewise function, right? That's usually one of the cases. If we cannot find a continuous function, it's most likely some piecewise function. And it's been a while since I've worked on these types of problems. Okay, so that's the function if my point is not the origin, or specifically if they're not zero. And then it's zero, obviously, if my if my x and y are both zero. Then it just means I'm at the origin in my 3D space, right? Okay. So you can verify that its partial derivatives exist at the origin. Let me actually do the picture and see. I can't really. So here's a picture of what the surface might look like if we were to graph it out. It would look something like this, like that. And the idea is that, well, partial derivatives exist at the origin. I can't really see it, but this is the origin. And we're saying partial derivatives exist, question mark. Okay. In fact, f sub x is 0, 0, and f sub y 0, 0 is 0. But f sub x and f sub y are not continuous. And so the linear approximation would be f sub xy is approximately 0. But f sub xy, I keep saying f sub xy, fxy is 1/2 at all points on the line y equals x. Can't really see that myself. So a function one half at all points. I can't really see that. Anyways, so a function of two variables can behave badly even though both of its partials exist. And so to rule out such behavior, we formulate the idea of a differentiable function of two variables. Right? I mean, I can see it behaving badly because right now I can't understand the picture. That's how much badly, that's how worse it behaves, actually. Yeah, it's hard to visualize everything in 3D. Um, but whatever. Okay, so we want to formulate the idea of a differentiable function. What makes a function differentiable? How can we determine if we can take the derivative of a function? That's what differentiable means, right? So that we cannot get this messy behavior of variables. Okay, so um, to hmm, to prevent bad behavior of variables, well, we're going to ask what makes a function in general, whether that's a single variable or multivariable function, what makes it differentiable? So I guess if we're given in one variable, y equals f of x, and we're saying if x changes, right, from some a value, from a all the way to a plus change in x. I don't know what that is. Um, well then that also changes our y, right? So we plug in this new change of our x value, a plus delta x, minus my function at that initial value. So that's how we can determine our change in y, right? And this makes sense in real valued functions in calculus 1. Um, and so they actually showed this idea of f being differentiable in chapter 3. So this was a very, very old idea. Um, yeah, it's being precise with limits in this case. So we're saying that, okay, if f, how can we say it's differentiable? If f is differentiable at a, we're saying if f is differentiable at a, meaning we can take the derivative at that point a. Well then, here let me write out important stuff. My delta y, or my change in y, is the derivative at that point. Delta x plus my epsilon at delta x. And what happens here? So to be precise, my epsilon goes to 0 as my delta x goes to 0 as well, right? Now let's consider a function of two variables. Now let's go back to calculus 3. Z equals f of xy. And suppose x changes and y changes. And x changes from a to a plus delta x. And y changes. So now both independent variables change. So from b all the way to b plus some delta y. Then we have the following. We have our increment of z, which is that function where we change our x, as well as when we change our y, minus f of a b. So here now we're just considering the other idea, right? Now we're changing two things, not just one. Then we can also use that epsilon idea. And so the idea here is that, well, z also changes when both our x and y values change. And so by analogy with our fifth definition, well, we can define its differentiability as follows. So let me just do that. So to determine if it's differentiable, well, we're going to say if my z is a function of xy, then my f is indeed differentiable at AB if, let me just write it out, if we can express z in this form. So my partial with respect to x, delta x, instead of derivative, we call it a partial. My partial with respect to y, delta y, and then my epsilon, I guess epsilon sub 1 in this case, and then my epsilon sub 2. Right, now we have two of those things. And we're saying that epsilon 1 and 2 are functions of delta x and y. And as they approach 0, well, my changes in x and y also approaches 0. So we're saying my epsilon 1 and 2 are functions of my changes in x and y. And the idea being, if we change our x and y, well then my epsilons approach 0. Right? And that's the idea. That's how we know for sure. Okay, I can take the derivative. I can take the partial derivatives of a function or of this point in the surface. right? So that definition says that a differentiable function is one for which the linear approximation is a good approximation when our xy point is near b. And so, in other words, the tangent plane approximates the graph of f well near the point of tangency. It's honestly sometimes hard to use our definition directly to check the differentiability of a function. So we're going to provide something more convenient to check if it's differentiable. So here's the theorem. Here, this is something easier to use. So good Lord, they gave us this complicated thing when we have this easier thing. So if the bottom line is if the partial derivatives f sub x and f sub y exists, because at the end of the day there are limits, right? And they exist near these points a, b, and let's say they are continuous, at that point, well then it's differentiable. So that's the idea. If the partial derivatives exist, if it's continuous, it's differentiable. We don't have to worry about that precise definition of a limit. But if you guys know this, then well and good. Then you have more of a deep mathematical foundation of how exactly or what exactly makes a function differentiable. But honestly, for beginners like myself, I don't know epsilon. I didn't study that. I'd probably use something like this, like a checklist. Can we derive this? Is it continuous? Continuous meaning, are there no holes? Are there no gaps? Are there no sharp points? Right? So I just use this. Okay, so let me do another example and then we can attack some problems here. So if it shows a limit definition, hopefully not. I could do one like in my spare time just to show or how to define that something's differentiable in the most mathematical way possible. Um, but we'll see. I'll just do it when I want to. Okay, so we are asked to show that my function of two variables, and in this case, it's an exponential one, x times e to the xy. Is it differentiable? I'd probably just use a computer. I'm kidding. Is it differentiable at this point? And if it is, find its linearization. Right? Then we're going to use it to approximate that point, f of 1.1 and negative 0.1. So most likely this is a differentiable function. Why? It's a polynomial. Any polynomial or elementary functions, any elementary functions should be continuous in this case. So we're going to approximate 1.1 all the way to negative 0.1. So I guess the first thing we can do, right, is, well, I mean, when we really don't know how to do anything, we just take the derivatives. So here, in this case, we take its partial derivatives, right? So let me quickly do that. Let's do it with respect to x. And so let me just set it up so that I can also do it for the others. So here I'm thinking of doing a chain rule, product rule, just in case. We're gonna add. Here I do a chain rule. And there, we're done with setting it up. Now, what is this? Here I treat my y as a number. I treat my x as a variable. So here I get e to the xy because there's just one. So copy 1 times e to the xy plus. Now what is this? We have x, copy x. We have e to the xy derivative, copy e to the xy derivative because that's the same thing. xy. Y in this case is a number. X is a variable. So this is just y, right? So we can say, just to make it cleaner, xy, e to the xy. Let's factor it out for fun. 1 plus xy. And we're done, right? So we've taken that derivative. Now, I don't know. Let's try doing it again for my f sub y. So let me just set it up. Okay, here I treat my x as a number. So this is 0. And so that means everything here is gone. X, e to the xy, good. Xy prime, I treat my y as a variable, my x as a number. So this is just y, right? Here it is just x. Here is y. So this is basically e to the xy plus xy, e to the xy. And so funny enough, I actually get the same thing. Um, that's funny. Oh, wait, no, I don't. What? F sub y? Did I mess something up? Oh, I get x here, my bad. Again, x here. Then here I go, y. Oopsies, my bad. And so, yeah, from there I get e to the xy plus x squared e to the xy. Oh, no, my bad. Not even this one. This one's gone. X squared. Yeah, I have to be careful with these sometimes. And from there, we just plug in. So we have 1, 0. Let's derive it. Does it work? 1, 0, right? Because those are my 2 points. And I plug in what I know. My x is 1, my y is 0. X is 1, y is 0. So here I'm just plugging in everything I know. This is 1. This is 1. So it's actually just 1. Right? That's just 1. Now let's do my y value. I'm going to plug in 1 squared e to the 1, y to the 0. 1 times 1 is 1. Now, by theorem 8, I'm not going to allow that theorem 7 anymore. I don't know why I wrote that. For theorem 8, do the partial derivatives exist? They do. Are they continuous? Yes, they are. Is f, then that means f is differentiable. So I'm going to say, since we don't have a solution, I'm going to write a paragraph. So by theorem 8, well, my f I'm going to say f sub x and f sub y exist. And f is continuous. So that means f is differentiable. That's your only checklist. You need two things. Do their partial derivatives exist? Yes or no? If yes, is the function continuous? If yes, it's differentiable. The moment your answer to one of them is no, it's not differentiable. Right? So that's the golden rule. I'm kidding. I don't know. I'll put like a little green check mark there. Okay. So let's now find the linearization. So how do we find the linearization again? Well, we actually have to find their tangent plane equation first, like what we did in the previous one. And then from there, we just automatically use that as our linearization. So we find the tangent plane equation and simplify, right? So let's find our tangent plane equation. So this is going to be z minus z naught. So at least I've memorized that part. Z minus, ooh. So here it looks like I don't see any z's. No z's. That's interesting. Actually, no, screw it. I don't think I need to. I just need to memorize this formula. There we go. F A B F sub x F sub y. That should be good. Actually, don't need to. So the formula is some L of xy. Uh, yeah, and then they're kind of lines in terms of x and b. So given some f a b, we're gonna add their f sub x and then their f sub y. Okay, let me be more. Yeah, and I usually forget formula. I just write it in red just because it's it's easier to look at or eye-catching when it's red. Okay, so can I find a formula for this thing? Do I have everything I need? Well, yes, I do. I have f of 1, 0, right? Uh, what else do I have? F sub x 1, 0, x minus 1, f sub y 1, 0, y minus 0, right? And then I have these values here for f sub x y 0, 1, 0, and f sub y 1, 0. Those are just 1. And so what else do I have? My f of 1, 0, I just plug it in here. F of xy, so this is, if I plug in my 1 and my 0, this becomes 1, 1, 0. This becomes 1. Whole thing is 1, right? So this is 1 plus, this is 1, so I just have x minus 1 plus y minus 0. And we're done. I'm gonna simplify. Yeah. This is 1 plus x minus 1. That's just a 0. So honestly, the answer is just x plus y. Let's just make it clean. It's just nice to look at, right? So that's the linearization, and that's what we're trying to find, right? And then after finding that, well, now we want to approximate. how do we find our linear approximation in this case? Well, it's the original function, right? So it's our f sub xy is approximately our L of xy. Now, I don't know why there's a help thing here. That's so weird. Okay. And then from there, well, what do we know? Well, we know x, our original function of two variables, is approximately x plus y. And then from there, now we can approximate these things. Right? So our f of, I think it was, what was the approximation? 1.1 to negative 0.1. 1.1, negative 0.1 is approximately my x plus y. So x plus y, which is equal to 1. So approximately it's 1. And if we compare the actual value, is, well, if I plug this into my original one, then I should get 1.1 e to the negative 0.11, which is around 0.958. So it's pretty close, or 985, right? Somewhere along those lines. Okay, but that's the idea of linear approximation. We're approximating something at that particular point, right? Okay, let's continue our homeworks and let's keep the ball rolling. Let's keep it going. We actually have like 3 more to go. So for number 5, right, because I did 4, here we're being asked to find the linear approximation of the function below at indicated point, right? Okay, let's do it. So we have my f of xy, 26 minus x squared, plus y squared, or minus, my bad, minus 4y squared, specifically at 1, 2. So let's find my linear approximation in this case. So the first thing we want to do, again, is to take partial derivatives, right? I'm kidding. Oh no, we actually do that. And then we just use the formula to get the linearization, and then we get the linear approximation. So those are our steps to doing that. Okay, so first we take partial derivatives. We actually have to do 4 things here. Respect to x, respect to y, then plug in for x and y. So my f sub x. So we take the derivative of this thing. What is this? Well, this is just, so again, when we're doing calculus, we want to translate them in kind of an ugly way, because that's going to help us use our calculus tools. So one of the ideas, right, is to take care of its square root. So we want to get rid of it. And then from there, let's just go at it. So we have 1/2 of whatever is in here. And then my 1/2 will be negative 1/2 because I subtracted 1. And then from here, I do a chain rule. I do a chain rule. So I get 1/2 square root of whatever was in here. I multiply it to derivative of this. So this is, now this depends on which one's constant and which one isn't. So here in this case, we treat y as a constant. And so this becomes 0, becomes 0. This becomes negative 2x, right? And there we go. Now we can cancel my negative 2. All right, just my 2. And so I get negative x all over this thing. And we're done, right? Great. Now let's do the same thing for my f sub y. So I'm just gonna write something a bit easier to grasp. There, I'm directly gonna write this, and then I'm gonna do the chain rule. Okay, I think that one's easier. So here this becomes a 0. This one is now a number. So my x here is a number. Now my y here is a bit different. I get negative 8y. And so from here I get 1/2 of whatever was inside. I think I should have used like a placeholder or something. And then this is negative 8y. And then I take this out. This becomes 1. This becomes 4. And so I have negative 4y over this thing. And that's my f sub y, right? It's a lot of messy computation because of this long term here, or long expression. But yeah, that's the idea. Okay, I'm just trying to make it a bit more organized. Now let's find it at these points. So my f sub x at 1/2. Well, I just plug in everything here. So negative 1 over square root of 26 minus 1 squared minus 2 squared. And I think that's it. Oh, minus, my bad. 26 minus 1 squared minus 4 times 2 squared. Yes. Okay. So this becomes negative 1. This is 26 minus 1, so 25 minus 4 times 4. 25 minus 16, which gives me a 9. So square root of 9, which gives me a 3. So I'm just left with negative 1/3. Okay. And then my f sub y. Well, now here I plug in, again, everything I know. So 4 times 2, my y is 2. This becomes 3 again. So that's negative 8 over 3. Great. And then from there, now we can find our linearization. So here we just plug in the formula. So L is equal to our F at the point plus our F sub x at that point, x minus A, plus our F sub y at that point, y minus B. And so that's going to be, well, L at this point. My F of AB, what is this? I just realized I haven't plugged this in. If we plug in a 1 and a 2 here, what do we get? We get 3, right? Because we just did it. We actually get 3 here. Okay, let me just do the complete solution. X minus 1. Y minus 2. Right? So here I'm just plugging in everything. Let's continue. Well, this is, again, 3. F sub x is negative 1/2. Or 1/3, my bad. 1/3 of x minus 1 minus 8/3, because that's my f sub y. And that's my linearization. And then from there, I find my linear approximation. And that's the idea that my function itself is an approximation of my linear, right? And so I just plug in what I know. So my function is this square root, right? So here I'm just really copying the steps. And I'm going to approximate that to my L function. Right? And so if I basically plug in for my f, and I plug this in my linear, I should get that linear approximation. So if I plug in 1 and 2, should be approximately L1 and 2, which I haven't done. Okay, for quicker purposes, next time I'm just going to automatically do this. 3 minus 1/3 x. So instead of x, I put a 1, right? Minus 8/3. Here I put a 2. Oh, voila, we got 3. That's my answer. So that's 3. My linear approximation of the function at 1/2, 1, 2 is 3. Right? Oh, my bad. Wait a minute. This is 1 and 2. No, I'm doing something. Oh, so for the first one, I have to plug in this function here. So I have to plug this in. That's one of my answers that I'm going to plug in. For the other one, I'm going to plug in so there was a given point that they want me to do, which is 1.07 and 1.93. And then here I plug it in here. Okay. And that should be, not super sure. Okay, let me just plug in the first one. I have to enter a number. Dang, that sucks. So I'm gonna use a calculator for that. So 3 minus 1/3 x minus 1. And then that's minus 1/3 y minus 2. And then I can use that approximation to solve for this one. So let me just quickly do that. What's this gonna be? 1.07 minus 1 is 0.07. Okay, let me just do it step by step. I got time. 1/3. This is negative 0.07. This is 3 minus 0.07 over 3. Oh. Okay. Wait. I'm gonna say 3 minus 0.07 over 3 plus 0.56 over 3. And I can simplify this even more. 0.56, I subtract the 0.07. So that's 3 plus 0.49 over 3. I could make this 9/3. This is 9.49 over 3. And if I approximate 9.49 over 3, I get, so I'm going to round it to 3 digits, that value, 3.163. Let me see if I got it. Should be the correct answer though. Nice. Okay, 2 more. Suppose we need to know the equation of the tangent line to a surface S. But we do not have the equation of the surface S. But we know some curves, right? That both lie on S. And so we need to find an equation of the tangent plane at P, right? So find, so here's the idea. Find tangent, did I say tangent line? I meant tangent plane equation of or not of, how they word it, to a surface S at point P. And this point P is 3, 1, 4. We're given these curves. And these are what we call parametric equations, right? These are vector functions. We did talk about these in a previous video in my calculus series. Okay. 4 minus 5t plus t squared. Ooh, that's quadratic. And then my other position vector that gives me the other curve are these things. 2 plus u squared, 2u cubed minus 1. And lastly, 2u plus 2. So how do I find my surface S? That's what I want to do. I want to find a surface S. I want to find surface S based on these curves, right? If I plug in a 3, 1, and 4, I should get the same point. or no, I should get my time when I'll reach this point. But how do I find the surface given these two curves or these two vector functions? And they both lie on S. Hmm. Okay. Well, I don't know. Let me check my other homeworks. Where vector functions? I think there was this idea. Sketch the curve, match the thing, find equation of plane. Oh, look at that. Find equation of plane with vector equation. Here I'm given two things. Here I check which one makes sense. Uh, Find a vector function that represents curve of intersection of two surfaces. That's another thing. Find the arc length. Okay. Well, we have two things. Not really super sure. Let me think about it. Um, I guess the first thing that we can do is to confirm that it indeed passes through P, right? We can do that. We'll get some parameter value out of it. And then what now can we do? We can compute their derivatives. So we'll get their tangent vectors to the two curves at the point. So we'll find our two vectors. That's one thing we can do, right? And we said that if we have two tangent vectors, it's on the plane. Now maybe we can find that normal vector, get the cross product. Then now we get that plane. Oh, so that one's super tricky, right? That one's really tricky. So okay, let me just walk through it. It's not really about finding the surface. So the idea was to confirm when curves pass our point P, right? So what's our T value going to be? That's one thing we need to try. 3 plus 3T is equal to 3, right? We can subtract T is 0. Let's look at another one. 1 minus T squared is equal to 1. Like obviously, we can just say 1 minus 1 is T squared. T is 0. Now we look at the last one. 4 minus 5t plus t squared is 4. Right? Here we can say t squared minus 5t is equal to 0. And then here we can say t minus 5 is 0. And then we can say t is either 0 or t is 5. And so the most common thing or common theme that we see here is that, okay, well, t is 0. Now let's look at the other one. 2 plus u squared is 3. So here I'm just checking at which parameter does this curve pass that point, right? 2 plus u squared is 3. So if I do this, u squared is 1. U is either plus minus 1, right? So it's either one of those things. Let's try another one. 2u cubed minus 1 is 1, right? And so 2u cubed is 2. U cubed is 1. U is 1. Right? Because 1, this is 1 to the power of 1/3, or cube root of 1. And this doesn't give me any negative value whatsoever. This is just u equals 1. So that works for here and here. And lastly, we have 2u plus 2 equals 4. We say 3u is equal to 2. U is equal to 1. That's it. And so indeed, it does pass here at t equals 0, here at u equals 1. Next step. After we know that, we want to take their tangent vectors at that particular point. So at point P. That's our initial point, right? And so we compute their derivative, right? And we plug in this parameter values after. So let's compute their derivatives. R prime of t sub 1. So we get the derivative of each component, function component. 3 plus 3t is just 3, right? What else? 1 minus t squared is just negative t, 2t. And lastly, 4 minus 5t plus t squared, that's 2t minus 5. And then we plug in what we know. We know that at t equals 0, it goes to that point. So we plug in 0 for my t value. We see 3, 0, negative 5. Then I go to my second position vector. I take its derivative. So I get 2 plus u squared, I get 2u. 2u cubed plus 1, I get 6u2, I think. 2u cubed, 6u squared. 6u squared. And then for 2u plus 2, I get just 2. And then I plug in my u value. Okay, I don't know why I put t. I put a different parameter here. I put u. So r prime of u, I get 1, right? When that position vector goes to that point, and then from there, I just plug in. So 2 times 1, that's 2. 6 times 1 squared, that's 6. And then 2. There we have it. Those are our 2 points, or 2 tangent vectors. And now we have tangent vectors. Yay. Now let's find, what do we need to find now? Well, we need to find a normal vector, right? The idea being, after we find that normal vector and that initial point, we actually have a plane. And that plane is, funny enough, that plane is the tangent plane. How do we know? Because we have the two tangent lines in that point, and both of those tangent lines are on the tangent plane. And so just finding that point and that normal vector, we can find the plane that's actually tangent, right? So let's quickly do that. So we're going to find this time a normal vector because we need that. And so we take the cross product of these two things, right? R sub 1 cross product with R sub 2. So this is again in a previous video where I take cross products. You guys might want to check that out first because honestly, we're far ahead in the course. Yeah, usually you want to check those first, the basics, before going into the complexities of things. Because that's how math works. It's kind of like solo leveling. If you guys watch that anime, you start from the very beginning, then you level your way up. Anyway, before I yap, so I do my cross product. This is 0 minus negative 30. That's plus 30. And then this is 6 minus negative 10. So that's 6 plus 10. And then 18 minus 0. That's k. Here I get 30i. Actually, let me just do it. 30i minus 16, 18, right? And then from there, I just write the equation of the plane, which is actually tangent. So right plane equation, actually tangent. And we're done. So I have my 30 and then my initial points. So my normal vector and my point. 3, 1, and 4. So x minus 3, y minus 1, z minus 4. And we're done. Right? 30, 16, 18. Yeah, that's that. Okay, so that's the tangent thing. Okay, let me go back and do that real quick. So 30 x minus 3 minus 16 y minus 1 plus 18 z minus 4 equals 0. Right? Let me see if we actually got it. I hope we did. If not, then that's okay. Yes, we got it. Okay, number 7. So this is the last one actually, and then we'll call it a day. So here we're given a paraboloid. So it's a quadric surface. It intersects x equals 3 in a parabola. And then we're asked to find parametric equations for the tangent line to this parabola at a specific point. And then we use the computer to graph the paraboloid, the parabola, and the tangent line on the same screen. And then we use t as a parameter. So we have a paraboloid. This paraboloid is z equals 7 minus x squared minus 3y squared. And this intersects the plane. So this paraboloid intersects the plane at x equals 3. And specifically, it intersects it in a parabola. And now we're asked to find parametric equations in terms of t. In terms of t. For the tangent line to this parabola. Okay. Specifically at a particular point. So that's our initial point, right? We just need some sort of direction vector. And that's the tangent line that we're looking for. Um, yeah. So we just need to find a direction vector in this case that will kind of model our motion in that parabola. So I guess the first thing that pops up to my head without even looking at anything is to actually find that trace, that parabola. So I guess we're gonna find that intersection curve, which is a parabola. So let me actually do that really quick. So that's gonna be when z is this, x is this, z is just 7 minus 3 minus 3 squared minus 3y squared. And so that's going to give me 7 minus 3 minus 9. That's minus 5. And there we go. So here we have z is equal to negative 3y squared minus 5. That's our trace in the yz plane, or kind of yz perspective of 3D space. Now, how do we find, or how do we parameterize this thing? Now that's the issue. X is 3, right? Do we kind of, wait, let me think. Parametric. So we're going to find parametric equations specifically for this intersection curve. So I'm going to let z be equal to t, because my x is just 3 in this case. Oh, so for parabola. My x is 3. And so that means my y, or no, not my y. My z is equal to t. And so now I have two things for y. Ah, shoot. Yeah, that's one thing. Because I have a y squared. So that's an issue. How do I, because if I do this, if I parameterize ZST, now I have this. Then I just isolate, right? Then I have over 3. But then I have to square root it. So that's, is there an easier way? No, that one's hard. Okay, let me think. Let me think for a bit. Yeah. Okay, let's just look at the So we're being asked to find parametric equations for the tangent line to the parabola of intersection. Oh, so it's a tangent line. So it's not a tangent plane, right? So actually, I can kind of do this visually. We're given a paraboloid. It intersects. So a paraboloid would look something like this. That's 3D. It intersects at x equals 3. So let's say this was the x-axis. And it specifically intersects here. And then this curve, we want to put parameters so that at every tangent line, we can kind of denote them in terms of t. So we actually just need two things. We need a parameter for z and for my y. I already found the equation of that curve, that green curve. That one's this. But I just need to put parameters there, where if I plug in some parameter t, I get a corresponding point, right? So that's my issue now. So yeah, okay, so we find the intersection curve, right? Okay, let's also put x equals 3 here. And then let's parameterize. So x equals 3, y, okay, you know what? Let's do this. Y is equal to t. And so that means my z is negative 3t squared minus 5. Oh, there we go. We did it. Nice. But that's the parametric equation of the curve. Now we want to find the tangent line. How do we do that? Well, we want to take the derivative, right? So now we find that tangent line. So we take the derivative. So, okay, to be more precise, let me just do this. X of t, at any point t, there's going to be a 3. At any y, there's going to be a t. At any z, this is going to be negative 3t squared minus 5. And so if I take the tangent, if I get the tangent line by taking its derivative, well, I get x prime of t. This is 0. My y prime of t, this is 1. And my z prime of t, this is negative 6t. That's it. And then now I want to plug in my point. So, oh shoot, we totally forgot to do that. Where does it intersect 3, 2, and negative 7? At what t? Right? So we also want to do that. Let me do that actually. 3, 2, negative 17. Well, yeah. I just got 3 here, so it doesn't really matter. T equals 3, that's true. That makes sense. Y of t is t. When t is 2. So that's the one we need. How about when negative 3t squared minus 5 is negative 17? Well, I can take out the negatives, right? I can subtract. So it becomes a 12. T squared is 4. And so t is just 2. And there we have it. At t equals 2, we get these points. And so we just plug it in. X prime of 2, well, we just get 0. Y prime of 2, we get 1. Z prime of 2, we get negative 12. And so we have this vector 0, 1, negative 1. So that's the vector, tangent vector, right? So it's the tangent vector at that particular curve, right? And what's fascinating is that this is actually in 3D. So here our x is 0, our slope at that point in the intersection curve is negative 12, right? Our slope is negative 12. And yeah, now we have that point. We have our direction vector. Now we can find parametric equations. So here we basically have for our x is our initial point, so 3. For our y, it's, wait, what are my initial points again? 3 to a negative 17. Oh yeah, this is 3 plus 0d. And then this is 2 plus 1. So 2 plus d. And then my z is negative 17 minus 12d. And yeah, that's it. Yeah, so very complicated items here or problems. But yeah, um, let me just try and plug it in because I feel like, okay, enter them as comma separated lists. X is 3, y is 2 plus d, and z is negative 17 minus 12d. Minus 12. Yep, with commas. Okay. Let me see if we got that down. And yeah. Okay, that's it for this video. I hope you guys enjoyed and learned a lot, and I'll see you all in the next one.